I'm going to introduce our first speaker of the morning. So welcome everybody to week 4 of this workshop. It's nice to see some familiar faces and some new ones too. And it's my pleasure to introduce Kathryn Mann from Cornell University, who's going to be speaking to us on Anosov flows, foliations, and the classification problem in dimension 3.
Thank you. And thank you all the organizers for the invitation to speak here and to spend some time in this beautiful place. It's a treat. As you can tell from my picture, this talk is really about foliations in 2-dimensional and 1-dimensional foliations and 3 dimensions. And so it'll have a bit of a geometric topology flavor, but the motivating question actually comes from dynamics and has a beautiful classical history. So I want to tell you a little bit of that story also along the way. And I'm going to try and pitch this very much like a colloquium and do not hesitate to interrupt, ask questions as we go along. Okay, so Anosov flow, what is this? I'm going to give you the classical definition, which is going to look like calculus, but then we'll quickly forget all of the derivatives and just sort of remember a topological picture. So in the definition, and this applies very generally. It's something you could put on a manifold, just any smooth manifold with a Riemannian metric in any dimension. But in my pocket, we'll end up having dimension 3 by the end, so you can just imagine everything is a 3 manifold. So an Anosov flow. This will be my notation. So a flow is just like a 1-parameter family of diffeomorphisms in a sense of continuous movement. Well, it's a flow, or I should say non-singular, meaning every point moves on some manifold equipped with the Riemannian metric, with the property that there exists 2 transverse. Sorry, I want to give actually the differential definition. So let's do this. There exists an invariant continuous splitting of the tangent bundle of my manifold. So one direction is going to be tangent to the flow. So that's easy to keep invariant. All right. In a 3 manifold, these are all just line fields. They're one dimensional. Something called the stable direction, which is contracted. All right. And something called the unstable direction, which is expanded or contracted in the text. Okay. And what do I mean more precisely by contracted? So contracted means, let's unpack this. For all vectors in this contracted direction, I need some constants. So there exists some positive constants. So that for any vector in the contracted direction, if I apply my flow, so I push forward this vector, its norm is going to change. And it's going to be strictly smaller by a uniform factor depending on time. So this will look something like C e to the minus t times k, norm of v. This is norm for my Riemannian metric. I can just pick whichever one you want. If you have a compact manifold, it doesn't matter. It'll just change the constants. This is for all t positive. And expanded means exactly the same thing, but in the past. So I have a expanded vector. The cheap way to write this is the same thing. Equation. Now I need an absolute value of t for t less than 0. Okay, so that's the official historical definition. But the key takeaway or the key fact, which is actually a classical theorem in this case, is that if I look at the direct sum of 2 of these, so either the tangent direction plus the stable, or the tangent direction plus this unstable f of the u is for the expanded direction. These give me now three manifold two-dimensional distributions, and these are integrable, meaning that they're tangent to foliations. Okay, which I'll call the S stable foliation and the U unstable foliation, respectively.
Hey, Katie,
Yes.
what are the dimensions of these? So I know you said three, they're always, each of these is one dimension, but what's the?
In general, it can be whatever.
But they're not,
So this direction is always one dimensional.
right.
And the general definition of an Anosov flow is that, is that there's some, you know, k-dimensional and some transverse, and plus one minus k-dimensional. So yeah, or minus one, oops, yeah, do the thing where they add up, and minus one minus k-dimensional. And this fact is true in all. Okay, so out of something that looked like a calculus definition where I had some expansive contractive behavior, you know, this is like a matrix, some kind of continuous time version of like a matrix where the eigenvalues are off the unit circle, right? I get this sort of foliation living on my map. So this is kind of the picture where I've shown you here, a leaf of the stable foliation in blue. So the transverse direction, so these are the orbits of my flow. And the transverse direction, you take a transverse segment and you flow it forward, its length sort of uniformly shrinks, right? And the reddish pink leaf is the opposite, where if you go backwards, the transverse direction shrinks. Why are these interesting objects to study? Actually, let me give you some examples which will possibly answer this question. Okay, so the first example is if you take your manifold to be the unit tangent bundle of some negatively curved Riemannian manifold, and you want to understand geodesic flow. So what is geodesic flow? So I have my, and then I'm going to draw it like a surface or something like this. And I'm looking at its unit tangent bundle, which is now going to be three-dimensional, which is the dimension I care about. Geodesic flow takes a unit tangent vector, and you know, what should I do? I should look at the geodesic that's tangent to this, and at time t, I'm going to move distance t along, and if that vector was v, this new vector is phi t. Right. So that's a well-defined one parameter family of diffeomorphisms of my unit tangent bundle. And if your manifold happens to have negative curvature, your flow has this property that you have these transverse directions of expansion and contraction, right? You can kind of imagine this, like here's a nice cartoon of some negative curvature piece, right? In general, if I take two nearby vectors, they're going to spread apart at a quick rate. But if you're very, very careful, you could hit that contracted direction. Yeah. Here, if you're an expert in these kind of things, or you do some hyperbolic geometry, or this is familiar, here the foliations that I mentioned before are the horizontal foliations. Okay. And this is maybe a familiar setup for some people. If it's not, no worries, because I'll give you a completely elementary by hand example instead. And so this is example number 2. So here's a way to make a three manifold and put one of these objects on it in a very elementary fashion. So I'll start with matrix, just a 2 by 2 integer matrix. So I don't know, maybe my matrix is going to be like 2, 1, 1, 1. And all I care is that it's in SL to Z, and that its eigenvectors are off the unit circle. So there I have a nice direction of expansion and a direction of contraction. Okay, that's my tool. My manifold is going to be the mapping torus of this map. So I'll take, oh, sorry, I haven't told you where this map is. right now it's just a linear map on R2, right? This acts on R2, but because I put it in SLTC, it converts the integer points. So it descends to a map on the torus by quotient by integer translations. Okay, so I can think of this as a diffeomorphism of the torus. Okay, and now I'll take the mapping torus of this diffeomorphism and call that my three manifold. So here's my three manifold. So I should take, here's a picture, here's my torus. I'm going to take its product with an interval. So I'm here. This is like pretty good, but I think I still prefer chalk. Good. And then I'm going to glue the front to the back. This is where we're the torus, right? So I already glued top to bottom and side to side. I'm going to glue the front to the back with my map A. So the way I've drawn it is I quotient by this equivalence relation where, let's see, x comma 1 is equivalent to a of x 0. It's just the mapping torus of this map. Okay, so that's a three-manifold. What's my Anosov flow? I'll draw you a picture of the orbits. I'll use a name for this. They're just going to go in straight lines across at unit speed. Yeah. Okay, and of course, when I get to the end, that point is identified with some other point over here, and I keep going. So phi t of like x comma s is going to be x s plus t, but this is all like mod my equivalence, right? So if I hit something above an integer point, I apply a however many times I need to get that. So just a straight line. Okay, how do I get these transverse directions of expansion and contraction? As you might guess, this just comes from the fact that I have eigendirections for my matrix. So if I take 2, 1, 1, 1, I think the contracting eigendirection is sort of sloped this way, right? So let's say first that I have two invariant foliations. If I take a eigendirection, this gives me like a line field on my torus. I can take the product of that with the interval. Now I get a foliation on my three manifold. And this is invariant, right? Because at the back, I just apply A to move the back side to the front. So some line in this direction will get moved to another line in the same direction, not the same one. But they'll glue up together, and this defines a nice two-dimensional foliation of this function. That's invariant under my flow, so I'm just going straight across. And if I take, say, two orbits that are on the same leaf in the, if I got this right, and this is really the contracting eigendirection. Well, if I apply my flow, maybe I'll draw this one in red or something. Okay, so far this looks bad, right? Because they're actually fellow traveling each other, they're not getting closer. But this picture is a lie. It's not an isometric picture, right? A is not going the front to back by an isometry. So whatever I've drawn here is not actually, showing the correct Riemannian metric or anyone that makes sense on this manifold. But what happens is I apply A, this segment, if it's in my contracted eigendirection, will go to a smaller segment by a factor of eigenvalue, whatever it is, with root 5 and f to this matrix. And the two orbits will continue to fellow travel, but much closer together. Right, and I iterate and we go forward in time, they'll eventually approach. And then uniform contraction comes from the fact that, well, A has a uniform rate of contraction as you do. Okay, and of course, transverse to this is the other eigendirection, and then you get the whole structure that I will show you in this picture. And of course, there was nothing special about 2, 1, 1, 1, right? Anything in SLTC would have worked, and if you think like higher dimensional examples, this is a nice way to produce a big family of examples. Okay, so here in the great history of things, we've arrived at about the end of the 1960s, where this was kind of the state of what was known. let me do a little history. Okay, so who was it, Anosov, or what was he doing in the 1960s? So in the 1960s, Anosov was studying properties of geodesic flow on unitangent bundles of negatively curved manifolds. So this is always assumed negatively curved. And this is a thing you do in differential geometry, you would understand the global behavior of the system that tells you something about negative curvature. He shows that this family of examples has a remarkable property called global stability. Which is extremely beautiful. So if you take, let me tell you what global stability means. So here's the theorem, the global stability theorem, is that if, say, phi is geodesic flow on something that looks like the unit tangent bundle on a manifold that's a unit tangent bundle of some negatively curved manifold, and I take another flow that is arbitrary. I forget that there was a metric or anything, but I just want it to be some little perturbation of the first one. So C1 close phi. So this means if I think about the vector fields that generate these flows, we'll live like at point by point the vector field of phi. Well then, actually they're the same, or they look the same to a topologist. There exists homeomorphism that takes orbits of one to orbits of the other. This is like the best thing you could hope for, right? There's two trivial things you could always do. You could always sort of like rescale time. You have a flow, you have this continuous motion. You could say, well, I actually have this little patch go a little faster. Right. So you can't expect to have something that is at the time that's a small perturbation, but the orbit's going to move. Right. And the other thing you could do is you could also just, conjugate, do a little change of coordinates, change the picture a bit. And this theorem says that if you're looking at geodesic flows, this is all that you can do. Okay. This idea is so important that it has a name. Okay. So if this holds, we say definition. Phi and psi are orbit equivalent.
So is this weaker than being topological or like smoothly conjugate to each other or something?
This is weaker because time change can't be achieved by conjugacy. And also I only insist on a homeomorphism, right? Which is like part of the reason why you have like Heisenberg space and stuff like this, all of these things that are like topologically conjugate, but actually in the sense that we're like a vast, forget Heisenberg space, vast space are very different. One recipe is change the Riemannian metric, right? And this will change like the light spectrum or whatever, but from a topologist perspective, like the behavior of the flows is the same. And so question is like topological entropy or something like great question. Okay. So this gives this great headline for two things. One is that all he used really about geodesic flow was the definition of an Anosov flow that I gave on slide 1. So retroactively, you can run his proof for any flow that satisfies that definition. All right. So the first, the suspension construction I gave you also has this problem. And of course, then you want to know, like, all right, this is interesting. What are all possible examples this applies to? And other than curiosity, the reason you might want to know all the possible examples is that this is a very interesting juxtaposition of like stability and chaos. We have this global stability theorem that says that as a whole, the system can't be easily perturbed. But if you look at individual trajectories, they're very chaotic, right? So here's my cartoon of negative curvature, and if I take two nearby tangent vectors, the fact that I have directions of expansion mean that their trajectories will typically like diverge completely wildly. This individual orbits are very sensitive to initial conditions, but the whole system is globally stable. So this is a beautiful juxtaposition, often called, you know, global stability, but local chaos. Yeah.
Your suspension thing reminds me a bit of the irrational torus, where depending on the slope, it's irrational, but it's like dense, and it's rational slope, and it's not. So that seems very different behavior from your flows to the. How does this relate to what you're?
Yeah. So so you're just sort of changing the slope of the foliations, right? But somehow the way the suspension construction I gave is very sensitive to the fact that you needed a matrix of F of 2Z to make it work, right? And those aren't easily perturbed. And so what you're sort of saying is, well, one thing that will never occur is if you try to build an Anosov flow, say on a solved manifold, there's something that you could realize as a mapping torus, you'll never have, actually in no case will you ever have kind of closed leaves of these foliations. Yeah. Okay, so this is like a weird juxtaposition of contradictory things. What we would like to know is this phenomenon extremely rare, right? Maybe we can make a finite list of all examples in the world, or all types of examples. Or perhaps it's like pervasive in the universe, and we should go looking for it among systems that. So this was a question raised by Steve Smil in his 1966 ICM address. He asked to classify all of such examples, and at that time, basically all that was known was geodesic flow and suspension. So you're up to date. The fact that you have global stability, though, means that whatever classification, it should be essentially discrete, right? If you have fine complete invariants, they should be discrete invariants because small perturbations don't change this, right? There can only be, this is a little argument you need to do, but there can only be like countably many examples in existence at all. Okay, so hence discrete algebraic or numerical invariance is what we're looking for classification. And I added a word that I didn't misquote Smale. This is transitive, and so I should tell you what this means. This means that some orbit, some trajectory of my flow is dense in the free manifold. This is not true. You have sort of attractors and repellers, and you can, even at that time, it was known that there's, you know, thanks to some work of Smale, that there's a way to maybe decompose it into more basic pieces. And so, you know, the first thing to do is understand transitive examples and then start to come up with some assembly process basic pieces into more complicated objects.
So it's Smale question just for Cornell? It's like you wrote it?
No, general. And for real history, there's a version of this that's like just iterating the matrix for discrete time things. And Smale at that point had a conjectural picture that situation is very rigid. It's all essentially just like integer matrices iterating. You have to be a nil manifold, you have to look like it's that kind of thing. This conjecture is now almost proved. It's proved in many special cases over the years. But for the flow things, he has no conjectural picture, nothing, just a statement that we should obviously be working on this problem. Okay, so that's where we are. And now we're at present day. And the first thing is that, so let's get up to now. So the first thing is that there are many examples that are not geodesic flow and not suspensions, but only on 3 manifolds, essentially. So in higher dimensions, there's one construction that gives you a couple more examples, and that's it. We do not know if we have reached the end of the list, but in dimension 3, it is the Wild West. So they start in the 1970s, actually, with work of Handel and Thurston, Sue Goodman, David Fried, using various surgery techniques. Where you cut along, so maybe you find it like an annulus transverse to the flow. Cut your manifold along this annulus and re-glue it back together with a Dane twist. So you change the topology of your free manifold. You still have a flow on it because you know orbits to orbits, and then you have to work very hard to show that it keeps this Anosov property. Right. So all of these change your manifolds. You know you've got something different than what you started with, and so you produce a new example. So this continued more and more sophisticatedly through the 1990s. Quite a library of examples was produced. But every time you sort of did one of these surgeries, you change your free manifold. However, it's even more interesting than this. It took until quite recently, so what year? I think it's 2015. In 2015, Bonatti and Hugh showed that the following theorem: there exists, for any number, 100,000 say, there exists a three manifold, compact three manifold, okay, with at least m pairwise non-orbit equivalent Anosov flows on it. So even if you fix your target manifold ahead of time, trying to come up with some invariant that classifies all the possible Anosov flows on that one three manifold up to orbit equivalence, this is already an interesting term. Their construction used sort of surgeries along tori transverse to the flow. So you might ask if you can do this in atoroidal manifolds. And with Jonathan Bowden, around 2022, we did the same question for examples of atoroidal, or admitting a hyperbolic structure. So if you give me a number, I can produce like a hyperbolic free manifold with at least that number of non-pairwise orbit equivalent Anosov.
So in those examples, do you know that there are only finite scenarios?
Here's a great open question. That's extremely important, actually. Does there exist three manifold, compact three manifold, with infinitely many, pairwise non-orbit equivalent? I'm using OE for orbit equivalent Anosov flows. We do not know. I've heard some people think the answer is negative. I do not. I don't. That's maybe wishful. So anyway, so what we really would like is nice invariants to distinguish them. Okay. But I guess I should say that there are examples where the situation is very rigid. So if you take the unit tangent bundle of a hyperbolic surface, that's a three manifold. Thereby, theorem of Schiess, there are only finite remain. In fact, I guess two are out to orbit equivalents. But typically, the situation, if you have a kind of a complicated three manifold, it can be very, very rich. Okay, so maybe to reiterate, there's maybe two parts of the classification problem. Right? Which first, there's like which three manifolds even admit any Anosov flow. Okay, this has been worked on and is relatively well answered, although we still don't know the total picture. And then the second part, which I'm kind of hinting at here, is very interesting, is that if I fix a three manifold, give some invariance, a la Snail, can be used to distinguish flows on this three manifold up to orbit equivalence. And it's this second one that I'm gonna. Other questions? Okay, so let me give you one sort of very basic invariant towards this. Here's sort of the most simple thing you could do. So I have a flow on a three manifold. Here, three, I guess, is not important. I have a flow. Sometimes some orbits will come close up and be periodic and make circles inside my three manifold. So the flow gives me a bunch of loops. I could write down all of these loops. I guess they're free homotopy classes because they're not based anywhere. So let's just write down this list of loops. So here's my definition. I call it, so here phi p is a flow. We define the periodic data, periodic, or it's a periodic orbit, it goes round and round. P of phi is just what I said, it's the set of loops gamma. So now I think of its free homotopy class up to conjugacy. And if you think of my definition of orbit equivalence, I just wanted to send orbits to orbits. I didn't really care about direction the flow was going. So I better not have something that's sensitive to orientation of this loop. So I'm going to record this if either gamma or it with the reverse orientation is represented by a periodic orbit. So that's kind of the first thing I could write down. I don't care if these are linked or unlinked or if they're not in or anything like this. I'm not counting multiplicity, I just want a list of free homotopy classes that I see. Okay. Easy observation, right? If I have an orbit equivalence between flows, so I fix my free manifold, have a map. If this is an orbit equivalence between, say, phi and psi, well, then what happens to the periodic orbit spectrum? They look the same up to whatever H induced on free homotopy classes. In particular, if you were isotopically identity, these are literally the same. And a theorem that I proved with Barthelm&eacute in some cases, and then in the remaining cases joint also with Stephen Frankel, is that this is essentially, in many important cases, this is essentially a complete invariant. So this is with Barthelme and myself, and then also later with Frankel. And I'm going to give the version with an extra hypothesis that makes it easy to state. So that will look at literally the converse. So if you have a three manifold that is atoroidal, that's my extra hypothesis. And I have a flow, which is, or I have two Anosov flows. And I want at least one of them to be transitive. Let's say phi is transitive. This is Snail's setting. If there exists some, I don't know, H automorphism of the fundamental group of your three manifold, so that H of the periodic data of one flow is equal to the periodic data of the other flow. Or I want said automorphism of fundamental groups. So there's a reduced map on conjugacy classes. Then phi, psi are orbit equivalent. They are the same by some map H, such that, you know, H induces big H on pi 1.
I have a question here. Assuming they put it, are these also prime or are they?
So yes, the classical thing I didn't put in my history introduction. If a three manifold admits an Anosov flow, then it is irreducible.
Okay.
Yeah, aspherical. This goes back to work of Planck and maybe Verhofsky in the early 60s. Yeah. Yeah. So great. Everything is irreducible. And then what's interesting is like looking at the JSV decomposition. Okay, so hopefully my previous thing said that even for H-orbital three manifolds, it is important to try and distinguish because there might be arbitrarily many. The real theorem here is actually there is a complete invariant, which is only slightly more general than this. So let me make a little edit to my statement. All right. Which you can ignore if you're parsing this for the first time, and you can think deeply about it if you like, you know, JSJ structure theory, whatever. So now this is for completely generally, if this plus something that I'm going to wave hands at and not define because it would take 5 minutes and I don't want to lose everyone. So and for the various cipher fibered pieces in the JSJ decomposition of M, something that we call the sign is really just a plus or minus that you can read off the dynamics of the flow, agrees. Then the conclusion is true. So in the completely general case, there's just a finitely much more data that you need to give a complete input. For the experts, there's a generalization, or for the people who are curious about this kind of stuff, maybe I'll make a quick remark, is that there's a generalization of Anosov flows called pseudo-Anosov flows. This theorem is also true for pseudo-Anosov flows. So if an Anosov flow is kind of modeled after my suspension example of a linear map on the torus, if you take a pseudo-Anosov mapping class on a surface of higher genus, and you take like the Nielsen-Thurston representative of this, so there's invariant singular foliations that are expanded and contracted instead of invariant genuine foliations. You make its mapping torus. The same construction gives you the paradigm example of a pseudo-Anosov flow, and you can write down a formal definition of what this X could be, which gives you a wide class and even wider class to study, and you can replace Anosov by pseudo in this statement, and it's the same thing. So in the rest of this, I want to give you maybe like a little hint. Well, actually, let me check if I said everything I wanted to say so far. I want to give you a little hint of the tools that go into this. And picture, you know, how do you think about these options? Okay, so this brings me to maybe part 2, which is part 1 was the classification problem. Part 2 is a tool called the orbit space. The main tool to prove this theorem. And this actually comes from work of Thierry Barbeau and Sergio Fenley in the late 1990s, around 1995, 2000. So at this time, they were both working on trying to understand Anosov flows in three manifolds up to orbit equivalence. And if you want to understand, you know, this problem is really asking you, what is up to homeomorphism, the one-dimensional foliation of your three manifold by orbits in this special setting. Right? So you want to understand this tangled mess of one-dimensional things in a three manifold. If you have something complicated in a in a topologically complicated space, it's much easier to work equivariantly on the universal cover. And so let us do that. So here's going to be some setup of how to think equivariantly on the universal cover. So given flow and an Anosov, let's say V2 on some three manifold, I can lift it just by lifting the vector field that generates it to the universal cover. Okay. And its invariant foliations will lift to invariant foliations. Maybe I'll give them little tildes as well on the universal cover. And as I mentioned in response to Andy's question, right, the universal cover, my three manifold is aspherical, so this is really just R3. Okay, and it is also classical, that comes from this dynamical picture, that no closed orbits are homotopically trivial. This comes from the foliation result of Heffler and Novikov. So in the universal cover, the orbits of this lifted flow are just all lines. Okay. And to make my picture simple, I will just collapse all these lines to a point. So here's the definition. The orbit space, kind of maybe not the most obvious name, but what's called the orbit space of the flow is just, I take the universal cover and I collapse every orbit of the lifted flow to a point. All right, and of course, since my foliations came from unions of orbits, this is where I wish I had the other board with this picture that I had right at the beginning. You know, leaves are foliated by orbits. The foliations descend to two-dimensional, sorry, to one-dimensional. They were what, two-dimensional? These one-dimensional foliations. Well, I guess they would if the space was remotely reasonable, right? You always have to worry when you capture a quotient, maybe you've got some horrible non-historic garbage. Here's the theorem due to Fenley, which is that topologically, this is a plane. The quotient is Hausdorff. Yeah. Once you know what you're looking for, this is not too hard to do. And so these are genuinely one
Both when?
there's actually an irregularity that comes from the flow. There's a local C1 structure. Yeah, so it's a C1 plane if you like, but I only need that it's a topological plane. And I didn't present it this way, but because it's a little more complicated to state, but there's a notion of topological Anosov flow, which really only is defined in terms of there's some invariant foliations with orbits that approach and forward or backward time. And you can do this with no different infrastructure whatsoever.
To just figure.
Hmm?
Oh, okay. Topological foliation.
Yeah, the topological, yeah. So this space is a plane. And so I have some plane with two one-dimensional transverse foliations. What does this look like? In the suspension case, this is a nice one to do just by hand. I get the plane with like its usual, I guess I'll draw them horizontal and vertical. Usual product structure foliations. Maybe easier to see if you slope these like the eigendirections of the matrix. In geodesic flow, it is not a homeomorphic picture, but it's still fairly well behaved. This is another nice thing. So the easiest way to draw this is if instead of thinking of R2 as my plane, I take something homeomorphic to a plane like this infinite diagonal strip. Okay, it continues. And then I put the horizontal and vertical foliations on this. So it's different than my first picture because not every red leaf meets every blue leaf, right? Whereas in the standard product foliation, that is true. And this topological picture is what you get for geodesic flow. This is a fun exercise if you like low-dimensional topology and hyperbolic surfaces on the unit tangent bundle of a surface with negative curvature, any sort of NEGs. But in general, the pictures are completely impossible to draw. Okay, you will see examples where you have a sequence of leaves of one foliation that limits onto a non-trivial union of leaves. Okay, and this might actually happen at like all scales. Okay, and this will happen like in both directions with both foliations. So here's, I think I'm succeeding at drawing a transverse. Something like this. Okay, and this happens everywhere. And so it's a very complicated picture. Okay, why is this picture helpful though? Well, I reduced dimensions, so it's something simpler. And it's still equivariant, right? I said we should work equivariantly on the universal cover, right? My action of the fundamental group of my three manifold on the universal cover descends to this orbit space, right? Because the quotient, I'm quotienting by something that was lifted, right? So this is well defined. So the fundamental group acts on this plane, preserving, not leaf-wise, but these foliations, what should I call them? Maybe like normal F, U, F, S. Now the action is really only by homeomorphism. It's no more regular than that. Okay. And theorem originally proved by Barbeau is that this gives you complete information. This is all you need to know to classify flows up to orbit equivalent. Okay. Around 1995-ish also, which is, so let me state this carefully. It says that if these actions look the same, then your flows are orbit equivalent. Well, if and only if. Okay. So more precisely, phi t psi t are orbit equivalent Anosov flows. Remember my three manifold is fixed. If and only if there exists pi1 equivariant homeomorphism H from the orbit space of one to the orbit space of the other. Okay. And by homeomorphism, I mean that it also is a homeomorphism of these foliated planes. So it's sending the foliations for one, maybe I'll decorate with some subscripts, to the pair of transverse foliations. I'm allowed to swap them because I'm allowed to sort of reverse direction. But I send the pair to the pair. The way I've said it is hidden in the word equivariant is I have to think about what, the action of pi1 M3 might be twisted by some automorphism of pi1 M3 if my orbit equivalence is not isotopic to the identity, right? So you have to throw that in there. But if you want to just relax, say we're trying to understand the orbit equivalence up to things isotopic to the identity, and then this is, you just conjugate the two pictures. Great. Okay, so now I can restate the theorem just using this complete framework. And I have to understand now like groups, three manifold groups acting by homeomorphisms on bifoliated planes. Right. So here's the theorem restatement. Of the main theorem, thanks to Barbeau and Fenley, is that I need to translate what my periodic orbit set was. So, maybe I'll pause on my restatement for a second and think about what does it mean for, an element of my fundamental group, to satisfy that, it represents a periodic orbit of my flow. So what does that mean? That means if I think about the lifted flow of the universe's cover, I told you its orbit is a line, but downstream it's periodic, so there needs to be some deck transformation that moves this orbit along itself to close it up, right? So what does that mean? That deck transformation, if I collapse this whole orbit to a point, it's gonna have to be fixed by that deck transformation acting on the plane, right? So if I have something that's a periodic orbit, this is exactly equivalent to this thing acting on the orbit space of my flow, as a fixed point. And here's one reason why it was nice to not worry about what direction things go. Something has a fixed point if its inverse does. It's convenient to put inverses into my periodic orbit data set. Okay, so with this observation of how to translate this, I can now restate the theorem. So this is the Barthelme, Frankel, myself theorem. It says that if, let's say that you have, phi t, psi t on some toroidal, I'll do the easy version. And one of these is transitive, etc. If for the action on the orbit space, the set of elements now of the fundamental group, I'm not thinking about pre-homotopy classes, just elements of fundamental groups, such that this element acts with at least one fixed point on the orbit space of phi is the same set as those acting with fixed points for the action on the orbit space of psi, then, I said the same, so I guess the conclusion I'm allowed to make here is that phi and psi are orbit equivalent by some H isotopic to the identity. And if instead of the same, I say it differs by an automorphism, well, that's what your H was. So this is what we actually have to prove. If I have a group acting on a space and I record the set of elements, this is not a subgroup, this is something that have fixed points as opposed to acting freely. Somehow I'm supposed to reconstruct this space up to homeomorphism. The space is the plane. I'm supposed to reconstruct these foliations of it up to homeomorphism, right? And then I'm supposed to find a map that intertwines these two actions. Okay, so I'm going to only give you the tiniest hint of why this might be true in the end. So what we need to do, prove it, restating what I just said, is, given some kind of set of elements acting with fixed points on a plane with two transverse foliations, and we know a little bit about what the action looks like, at least kind of locally, because we can use something about the structure that it came from a three-manifold. We need to somehow reconstruct the foliations and the action, up to homeomorphism, up to conjugacy. Okay, so here's the cartoon picture of why this seemingly maybe impossible thing to do is possible. So if I have, let's talk about a single element acting with a fixed point. Suppose I did a bunch of work and I was able to show that, gamma acts on this plane. You could imagine even the trivially foliated plane with some fixed point. What does this look like? Well, okay, here's my fixed point, and I have through it the leaves of my two transverse foliations. What do the dynamics look like? As I iterate gamma, right, going along an orbit, some of the orbits approach each other on one of these leaves, and some diverge. Remember sort of picture number one from slide number one. On one of these leaves, I see approaching behavior, and on the other one, I see divergent behavior. This means that as I iterate, gamma is representing this action of the deck group moving me away. Some of the orbits will approach, so I'll see contraction along one of these leaves, and I'll see expansion along the other. This is also maybe, if you think of the suspension map, it's like you're iterating your 2-on-1 matrix or some power of it at a periodic point. It's exactly what you see. Okay, if I apply some other element of the fundamental group, I don't know, maybe I have an alpha. I can try and ask, where does alpha just send this local picture? Maybe I need a new page, so let me draw a picture. I'll repeat this part. Copy. See here, you can see my mental process that I'm going to just copy paste. Paste. What's alpha doing? So there's some possibilities of what could happen. So this is the fixed point of gamma. Alpha is going to move it typically somewhere else. And there's possibilities, right? The first thing that could happen is that I don't move it too far. And so the images of these leaves under alpha intersect each other. All right, second possibility is maybe actually this doesn't happen. So here's my gamma picture. And alpha moves it over here. And my plane was like only a little more complicated. It wasn't the trivial plane. These no longer intersect at all. And there's like a third possibility, which is that let me draw my picture before I talk. Here's a fixed point for gamma. That was the action of alpha there. Alpha moves it somewhere, and they partially but don't completely intersect. So one leaf intersects and the other ones do not. Okay. Yeah, I'm not worried about whether it's one quadrant or whatever, it's just purely combinatorial. All right. And the nice starting lemma, the babyest case of knowing fixed points determines the action is the following statement. It's that you can distinguish these pictures just by knowing like this periodic thing, the set of things that acts with fixed points. Okay, so picture one holds if and only if for all natural numbers, if I take some high power of gamma and I compose this, or concatenate it here in the fundamental group, compose it here thinking of an action with a high power of its conjugate by alpha. Okay, that's the element of the fundamental group. This acts with a fixed point. Okay, one direction of this is very easy. One implies this statement just comes from the fact that this point is fixed by this conjugate. I've written composition like function composition. The dynamics looks like expansion that way and contraction this way. Oops, sorry, I got it wrong. It's arrows that I can draw. This picture, I just moved my little picture over using alpha. All right, and so now you think about, you know, the set of all leaves that passes through here. It gets contracted by this one and then contracted by the other one. So by like the easiest version of Brouwer fixed point theorem, there's like an invariant leaf going this way for the composition. And then you do the same thing with the inverses and you get an invariant leaf going that way and you find a fixed point. The other direction is quite tricky. And even more tricky is swooping up this lemma and saying that actually the whole architecture of how these foliations intersect and interact with each other and how elements of your fundamental group acting here move them around is completely determined by the space point set. But that's much too much for a talk. So I'll conclude there and just say thanks.
Are there any questions for Casey?
Is it possible to say how many periodic orbits you have?
Yeah. This is a deeper question than you think. So the first I mean, maybe it's a big. So the first answer is there are lots. So for instance, one old result that now has a much easier proof, but an old result is that if the original, it's like Margulis-Thurston, if you have a manifold with an Anosov, a three manifold with an Anosov flow, then the growth of the fundamental group, or like volume growth of balls in the universe cover, is exponential. And one way you can prove that now, sort of retroactively, is just by showing sort of the set of elements representing periodic orbits grows exponentially. Okay, so lots, but I think it's a really interesting question to ask, like asymptotic behavior of this in like sets of three homotopy. Maybe you want to work on hyperbolic three manifolds because then you have nice representatives or something like this. What is this like asymptotically like 0%, 100%, like some fixed percentage, like proportion? Like I have no idea. I think it's a super interesting question.
You're recommending
Okay, how much do we know about three manifolds group actions on multiplying by homomorphisms?
Just generally,
Mhm.
not a lot. So here actually the three manifold group is not so useful. The fact that you have invariant foliations and expansion contraction directions is what we really use. And so this theorem actually, what we prove is some more general thing. If you have a group action on a plane with some invariant foliation satisfying like ABC, then this holds. Somehow classifying very general, I don't know. All these actions are faithful, yeah. Yeah, so in particular, you get lots of this. You know, we don't know very many examples of, say, like groups that cannot act freely on the plane. So like, is there some weird pathological action of a three manifold group where like no one has a fixed point? Oh, no one's, we don't, yeah.
So how, I assume big memory that there's some kind of classification of foliations of the plane involving like non-Hausdorff fundamentals. How arbitrary are these foliations?
Yeah. Typically the leaf spaces of both are non-Hausdorff.
So they can, are they special foliations of the plane, or are they very excited in the sort of pretty arbitrary foliations?
Oh, yeah, so this is an interesting question, is if, can any foliation of the plane, well, the only thing that's giving you some specialness is like this homogeneity where you have an action of a fundamental group of a three manifold, or you have an action where in this case from transitive flows, there's a dense orbit for this action.
Mm.
So you can't, so for stupid reasons, you can't take any non-Hausdorff one manifold because like if it's some long rooted tree and then branches, like this is no good. But something that branches everywhere, as far as I know, there's no obstruction. It's probably something.
Any other questions? Yeah.
If you start with the first trivial example, transverse foliation, if you draw a subset, a complicated subset, which is homomorphic to R2, and restrict this foliation,
Yeah.
is this a good example?
This is a good example of typically an inequivalent, you know, bifoliated plane. But none of, almost nothing you will draw will come from an Anosov flow. So because there's a way to make precise the fact that you have branching everywhere or not at all. Yeah.
Other questions? If not, let's thank you. For everybody, parts, just let me mention a couple of things. So if you've not already done so, take a photograph of your little menu and or otherwise commit it to memory. And then please give the slips back to me. We will have our next stop at 11:15, and there's coffee downstairs. And oh, I should say, dinner that you're signing up for is on Thursday. So some of you will have to do that. So Thursday is when we get to. Okay, thanks.